Welcome to Careless Coder. Today, Amiga-Assembly lesson 1 of I don't know how many. Motherfucker! So I have a lot of fun doing these videos on C64 assembly, but I've done that so often in the past and there are still 2 lessons coming, joystick control and sprites. But I wanted to continue on because I had a lot of fun, but then with the Amiga. I never owned an Amiga in the day. 2 years ago I bought 2 and I refurbished them and started a little bit of assembly programming. I did 68,000 on the trusted ST, but I wanted to know more, and that's when I bought this book a couple of weeks ago to really deep dive, really understand it. I did watch some videos of Scoopex, really great stuff, but a bit slow. So I will take up the pace as you're used to now with the Commodore 64 and the ARM64 assembly. And we're going to rely a bit on this book, although the examples that I create will be different than the book, they will be my own. That's also the only way to learn something. I highly recommend this from Mr. A.T.H. van den Oosterkamp, probably a Dutch or a Belgian guy. They are the best, right? So let's jump in and first get our toolchain installed, and then we will actually create 2 raster bars straight in the copper list. So we're really jumping deep into the book already from the beginning, because it's that simple. We can do that in 45 minutes max. So let's jump in and have some fun. Now before we can start Amiga programming, we need to install a toolchain. The first thing you need to install is FSUAE on when you're on Mac or Linux, or WinUAE on Windows. You don't need to configure anything. The configuration is part of the .vscode that I provide, and that the extension that we're going to install now will actually use. So we're going to use this awesome extension. Go to extensions, Amiga-Assembly. There we go, by Paul Reingaerd. Thank you, Paul. You install this, okay. And then what you do is Ctrl-Shift-P or Apple-Shift-P. And you do download binaries. Here, Amiga-Assembly download binaries. This will download the whole toolchain for you. You will see a little flash in the bottom. Okay. And then you can actually create a example workspace. Let's do that. Let's create that. Create workspace with an example. Development. Oh, it wants to actually run it in here. Let's do Amiga example. It needs an empty directory and the program name copper, because that's also what we use in my repository. And it will create an application for you, and it has the .vscode there already set up, and it will then start the application called copper in this case, same as in my case, because I just created this and started my lesson on that code base. And then right here, click on drop down on either WinUAE debug or WinUAE run when you're on Windows, or FSUAE run in our case for the Unix guys. And there you go. And this is actually something that we're going to be making in lesson 3, but we're going to make it more properly. We're going to use a sine wave instead of having those hard duck bounds. And now we're actually going to write some code. We're going to actually make some copper bars, and we do that from scratch. First going to close this folder. Then we go to a terminal. You can even use the terminal from VS Code, and you check out my repository, link below, Amiga lesson.git. Right, you go and open that project, open folder, Devil Amiga lesson. And we start at the copper.s file. And this is already in there. We're going to make this. Now that we have a working toolchain, let's start programming. I am following this book by Mr. Oosterkamp, and it relies on a save start function. And I really like that because it saves everything, opens the graphics registers, saves the interrupt enable registers, the DMA, con, etc. And then calls the main subroutine, that's where we put the code, and then restores everything. So that way we can safely start within Workbench. And this actually relies on all the names in the BareMetal.i. And the BareMetal.i basically has the same purpose as the HWI that comes from Paul Reingaerd's awesome Amiga-Assembly plugin. Thank you, Paul. But we are going to use the bare metal and the safe start. So we need to include that, include BareMetal.i. Then we need to open a section for our code. We call it code, and it is in the code section. Now you could be very explicit, code section _C, which is the same as code without, because _C stands for chip RAM. You can also do fast RAM, but obviously Amigas didn't come with fast RAM from the factory. So if you use fast RAM, yes, your code in your code section would be faster because it doesn't need to wait for the DMAs, but your code wouldn't be portable. And then we do an include and include bare metal, SafeStart.i. And we then go to the main and we do an RTS. And then we would need to save our stack frame. Now we could do this a lot of times, and I don't really like doing that a lot of times. So I also created a directory called vscode without the dot that houses a code snippet. So let's copy this because I don't want to do this boilerplate every time, even though it's not that much. Don't save, especially don't save, don't know what it changed. Go to preferences. On Linux and Windows you have preferences here. We need to go to preferences there, configure snippets, and then you see the list of all the stuff that your VS Code is currently aware that you can create snippets for. And you will need to look at the lower right what your current language is. So your language mode is Amiga-Assembly. So if we type Amiga-Assembly, we see it's actually the bottom one, m68.json. So let's copy this in there, save it, and then we can close it. And then when you do Ctrl-Shift-P or Apple-Shift-P, and you do snippets, insert snippet, that one, you see the snippets that you have, and start up, boom. Right? And this is something that you would do every time, assuming you use that safe start, which I advise you because it actually makes life a lot easier. Right? But let's write this code because this is important. 68000 uses the move command to actually move data into registers and move registers. And for example, we had STA on 6502, LDR on ARM64, and MOV on Intel. And we can move a byte, a long word, or a long word is 32 bits, or word 16 bits. Because all registers are 32 bits. They called the 68000 a 16-bit processor. I think it was actually a 32-bit processor with a 16-bit bus. Just like the 8088, I believe, that had an 8-bit bus and 16 bits registers, was also qualified as a 16-bit processor. We have some specials, move M and move quick. We get the nice description. We're going to move multiple registers at one go. We have 8 general purpose registers, data registers, and 8 address registers. And we can use all of them except for A7. A7 is the stack pointer. So we want to move the A to A6 onto the stack, and we need to subtract 1 every time that we put something on there. So D0 is put on there on the stack where the currently is, and subtracts 1, D1 subtracts 1, etc. Now we need to, and oh yeah, you could actually use A7 as well. But let's be clear to do that. And any good programmer, as soon as they allocate memory, writes immediately the deallocation code. And this does the reverse, where currently the stack pointer is pointing. It will put it, in this case, in A6, then add 1, then A5, add 1, etc. until it's to day 0. And the return from subroutine, we know that from all the other stuff that we did. And because I have that launch JSON in the .vscode, we can click on here and we can actually, you select run, otherwise you first have to click the debug. And it should start and stop. Yeah. Now you also see that we did this, load effective address $dff000 in A5. Now I found this very ironic. I never did a lot of, I never did 68,000 assembly back in the day on an Amiga because I had a Atari ST. And yes, the Amiga is better. I can admit it now after 32 years. But funny enough, the same work thing also is on the ST. That if you use a base address, you load it in A5 and you use relative addressing in relation to A5. And this just saves space. For example, we could do this. We can move FFF in $dff00. And let me insert that snippet for waiting on a mouse click. We'll explain it in a bit what it does, but just for demonstration purposes. Sorry, DFF 180. $dff 180 is actually the foreground color. Oh, it even tells you that, color 0. Right, so this should make it white. Yeah. But this also works, and this is smaller and faster code. Oh, I didn't close it. And this will also work. Okay. All right, let's do that mouse code. In the VASM, we use VASM 68K as the assembly here. That Paul Reingaerd automatically installed when we did the assembly download binaries for us. Thank you, Paul Reingaerd. Thank you so much. This is a local label with the dot. So if you have sub2 RTS, we can use .wait here as well. And you don't need a colon for labels with VASM. I generally use colons, but you don't need them. And then we do a bit test. 6 on address best friends forever 001, which is a special hardware register, and bit 6 is pulled up when you click on the mouse button or your fire button. But let's not use these. We have CAA PRA, which is CAA plus PRA, and let's prove in the BareMetal.i that that is indeed that address best friends forever 1. Where is my bare metal? I am looking for include. CIAA. There we go. That's best friends forever 1, I call it. And PRA is 0. And that's added to it for completion's sake in his macro. Okay. So branch not equal. We've seen that in a lot of assemblies. Branch not equal. And let's do a byte jump. If you omit it, the assembler will figure it out, but now we're definitely sure that it's a very short jump, and that saves bytes and is quicker. So branch not equal to .wait, so it will wait until bit 6 is equal, so 1. So we did this. Let's make a copper list. Now the copper list lives in a data section, so we call it data, and of course it needs to be the chip RAM. Like all hardware addresses, they need chip RAM in order to get to it. And like I said before, you could run this in fastmem to make your main program a bit faster, because with chipmem the CPU waits every other cycle for the hardware. Then it wouldn't be portable. And a copper list is just a list of basically data, and it has two instructions: a wait, a skip, and a loop or jump. We're now going to focus on the wait. So we're going to wait for a line 0, position 7. That is because we have that overscan, or we could just do 0, 0, should also work. And the wait instruction is FFFE. And we're going to set, and here this gets a bit tricky. Here we first set the color, or the register of the color, and that is 180 in this case, because these are only 16 bits wide. So the DFF is assumed by the copper, because the copper can only deal with all the hardware registers that are on the DFF plane, so to say. And now we have to tell it that we reached the end of the list. How do we do that? Well, that's also a wait instruction, but we wait for an impossible position. FF, line FF, is not an impossible position, because that is somewhere a little under half of the screen. But the with position FF is impossible. So there we go. And now if we actually load the copper list into a register A0 that's available, so we can then move that A0 into cop1, that is address 80, that's the first address. It exists of, as you can see, 80 and 82. Oh, cop1. And there are two copper lists. We're going to use only cop1, and that is also relative, of course, to A5, because it's, as the documentation says, DFF 80. And now we have to enable the DMA. So we do that with a move word. A0, not A9. Otherwise that would not work. Okay. Right. By the way, these are tabs that I use here. So 80, that is DMA enable, and we need to enable the DMA, which is on bit 7, that is 80. And we put that in the DMA control register, which is 69, in relation to A5. Now, how do I know that bit 7 was the DMA? If you hover over it, you see all the DMAs, and bit 7 is the coprocessor enable. Where was it? Here. Yeah. So now we should create a widescreen by the coprocessor and not like we did before by the CPU. So we should have the same result, but it's done by the coprocessor. Yay! Okay, now let's make a raster bar. So let's wait for a position. Let's do it pretty low down, so I can later create a second bar that is below line 255, because the student of you would have wondered, like, yeah, you run on PAL, so you have 512 lines. How do I get to line 512 if I only have FF lines? We get to that. So let's F0, position 7 on the screen. Let's give it a nice fuchsia color. Fuchsia. Sorry, I need to first wait, of course. $FFFE. Wait is... Oh. That is the only drawback, that you need to do escape. That is so stupid. Right, okay. So we're going to load color 0 with a fuchsia color. Something like that. Oh. 7. Oh my goodness, I need to drink something. Hang on. It's actually F7A. It was a typo. Some water. Right, and let's create a bar. So let's copy this to the next line. F1, let's make it a bit darker, F58, and F2, let's make this a nice blood red, F26, and I'm a bit annoyed already, so let's just go back, F3, and we want to have F58 again, and F4. Let's go back to that fuchsia color. Fuchsia. Oh yes, fuchsia. Right, okay. So this would create a nice gradiated bar. The astute of you will know already that something will go wrong. Let's run this. Boom. And this is drawn every frame. It's drawn automatically by the copper. How cool is that? You should have used this Atari, really. But yeah, we don't set it back to 0 at the line below, because we need to have that same background color. Oh. I bought a new keyboard, and I'm still getting used to the keyboard layout. So I'm even worse typer than normally. Oh, yeah, see, I'm often cracking the old now, because the keys are a bit wider. Okay, so now we should have a nice line. Only a single, nice bar. Yeah. Let's create a second one, and let's do that 20 positions down, 20 positions in hex below FF. So how do we do that? Well, we first need to wait for the last position on the first half of the screen. So that's FF, and then DF. This is the last position on the first half of the screen, or yeah, the first 255 lines. We have 512 of them. And now if we actually copy this, and we use, let's say, 20 as an offset, because then I don't need to type as much. 2 to 1 to 2 to 3 to 4 to 5. We should have 2 raster bars that are drawn automatically without the CPU every frame of the Amiga. And if you click, so yeah, that's writing your first awesome copper application on the Amiga. So there you have it. We created 2 awesome copper bars programming bare metal with some guidance of this book. In the next episode we will actually dive more into the 68000 assembly, where I will actually make these 2 bars seemingly rotate. It's not something that is in the book, but it's something that we did on the Commodore 64 and on the Atari ST back in the day. It gives a nice little illusion. And in the 3rd episode we will take that example that comes with the awesome extensions that Paul Reingaerd created. Thank you, Paul. And we make it actually a nice, smooth sine wave that it doesn't stop abruptly. And yeah, whatever comes after that, comes after that. I have a lot of ideas, so let's see. So I hope you learned something, and see you in the next one.